Below I present the project article entitled Laboratory Scale Method for Addressing the Problem of Mineral Scaling in Oilfield Facilities, as present corresponding order Eng Fermín Rosales Arias. One of the primary challenges encountered in mature oilfields is the formation of mineral scale, which is caused by formation water produced along with hydrocarbon. This generates economic impact resulting in high operational costs. Today, developing technological solution to control this issue is one of the main objectives in the industry. For this reason, an experimental methodology was developed that allows determining the scale potential of brine under dynamic condition, pressure, and temperature, as well as the inhibitor efficiency of chemical products. The most efficient inhibitors are based on copolymer, particularly derivatives of itaconic acid and sodium vinyl sulfonate. In the oil industries, the performance of chemical scale inhibitor is evaluated using the international standard NIST TNO 374-2015. The use of the standard presents the following limitations. It uses a synthetic brine with low scaling ion contents. It considers a temperature of 71 plus or minus 1 degree Celsius, atmospheric pressure, and a static test period. In a statistical study of Stephen Davis analysis of from formation waters, the calcium ion contents range from 3,500 to 199,000 ppm. Formation water is a byproduct of hydrocarbon production and contains high level of dissolved mineral that form scales, starting from the ion pairing followed by massive nucleation. It is also caused by the reduction of water volume due to evaporation, which decreases its solubility. In production, consists of hydrocarbons, formation brines, and emulsions. Emulsions are precursors to mixed scale. This is defined as a scaling solid composed of inorganic salt combined with a mixture of asphaltiants and resins. This methodology uses formation brines and or synthetic brine with scaling ion content similar to that of the fields under study. Consists of three stages. 1. Evaluate the inhibitor's capacity under dynamic conditions at constant flow rates, operating pressure, and temperatures. 2. The evaluation is performed using formation brines and or synthetic brines and or mixture of both. 3. The high aggressiveness of some brines, it is necessary to use a robust dynamic experimental. The experimental equipment has four positive displacement pumps, has two transfer cylinders that discharge into a coiled capillary inside a convection oven at the design temperature. This capillary acts as the nucleation point where mineral scale form. It is equipped with sensor that records differential pressure. As scale from the differential pressure increase, the system pressure is controlled by regulating valve. Experiments were conducted based on field operational conditions, using synthetic brine at 110 degrees Celsius and 500 psi. For each test, the experimental setup was calibrated by injecting distilled water. Figure 1 shows the equipment calibration. Table 1 and Figures 2, 3, and 4 present the experimental results. For the test, a duration of 9,000 seconds and a pressure drop of 2 psi were established. When evaluation the reference with synthetic brines, the pressure drop occurred at 452 seconds, establishing it at one order of magnitude. In the evaluation of the commercial chemical product, dosing 50 ppm of the inhibitor successfully extended the flowing time by 1.67 order of magnitude. However, when increasing to 85 ppm, performance decreased to 1.58 order of magnitude, indicating the maximum effect of the inhibitor. The evaluation of the new chemical product at 50 ppm doses showed that this greatly exceeded the performance of the commercial products, as it did not reach the 2 psi pressure drop in the established time. It was estimated by extrapolating the data that the flowing time was extended by more than 19 orders of magnitude. When evaluating the formation brine supplemented with anionic brine, it was observed that a 2 psi pressure drop was reached in almost 1,500 seconds. Conclusions. The evaluation of the new chemical product showed superior performance compared to the commercial product used. The dynamic experimental setup has the capability to reproduce the phenomenon of scale formation under field conditions and evaluate the performance of chemical inhibitors. The formation brine was necessary to dose it with an anionic brine to restore its mineral loss. It was observed that its scaling nature recovered. When comparing the results of the synthetic brine evaluation with those of the Dove formation brines, the result is similar, demonstrating that this use representative synthetic brine is feasible. Based on the results, the possibility of conducting an industrial test at an oilfield facility is established to evaluate the new chemical inhibitor product. Recommendations: the design of synthetic brine should be based on a comprehensive statistical study of the data generated from Davis analysis of formation brines from the field. When evaluating formation brine with low or no iron contents, the mineral load should be replenished using synthetic brine. Sampling of formation brine should be conducted upstream of the location for mineral scale physically forms. Experiments must be carried out under the specific operating conditions of the facility. I am grateful to the Mexican Petroleum Institute for the support provided at their facilities for the development of the experiment conducted, and to Emmanuel Marquez Ramirez for his valuable support and expertise in this test.